Well, ladies and gentlemen, I'm preparing a lecture on action potentials in nerve fibres, and I've come across a problem that I often come across with students and indeed some teachers about what I think is a misunderstanding, or at least a failure to appreciate the importance of accuracy in describing what happens when ions move across cell membranes. And this particular problem actually has three manifestations that conceptually cause problems. So let's take the example, I've got it on the board here, of sodium moving through a voltage gated sodium channel into an axon. And the problem then arises as to what happens to that sodium once it's travelled across the plasma membrane and into the cell. And often you see descriptions of the sodium ions moving into maybe the centre of the cell where they accumulate and give the positive charge that is the depolarization, and also some suggesting that the sodium ions then diffuse down the axon to carry the electrical charge. Now, what's the problem with these concepts? Well, first of all, there is this thing called the law of electroneutrality. It's not actually a fundamental law. It sort of is approximated, at least in biological solutions. And the law simply states that in a sample of a solution, the number of positive and negative charges is equal. And the reason for that is it requires an extremely large electrical charge, an electrical field, to separate positive and negative ions. So if you were to sample the fluid, either inside or outside cells in the bulk phase, there will be equal numbers of positive charges. So the simple idea that the sodium comes in and accumulates in the center without balancing negative electrical charges is, I think, straightforwardly wrong. So what does happen to the sodium when it travels across the cell membrane? Well, here actually the idea about what happens in wires to electrons to carry current is worth considering. So in an electrical cable, if you feed in electrons at one end, very rapidly electrons appear at the other end. The process is extremely fast. It at least in some wires under some conditions, approaches the speed of light. Now, is the suggestion here that the electron, when it enters the wire, whizzes along the wire at the speed of light to appear at the other end? Well, no, that's frankly wrong. What happens is, and now there are two hypotheses that you can choose from, is either that there is a charge redistribution with the electron that comes in pushing the other electrons a little bit along, so one pops out at the other end. And the other explanation is that the electron coming in generates an electrical field. And it is that electrical field that moves extremely rapidly along the wire, causing the ejection at the other end. I think the second hypothesis is slightly better, since it doesn't rely on the physical interaction of the electrons bumping into each other, which I think can cause a problem. But you can use either, and either works well. But what I think isn't happening is it's not the electron that moves in, moving along the wire. Instead, it is a redistribution of charge caused by the charge coming in. So now what happens to the sodium? Well, I think the sodium coming in causes the same charge redistribution to occur. So it's not the sodium coming in that moves along, rather it is the redistribution of electrical charges within the cytoplasm that causes the electrical potential to move along the nerve fibre, at least for a very short distance before it gradually leaks across the cell membrane. Now, I think there's a further refinement that we need to make here as well, because I think we need to stop at the point at which the sodium comes in as thinking of the charge as being carried by the sodium. So when the sodium comes in, because there is this law of electroneutrality, where does this additional charge, this additional positive charge that's unbalanced, that's coming into the axon, where does it go? Well, the best guess, and there's very good evidence for this, is that that charge accumulates on the inside edge of the cell membrane. In fact, it balances negative charge that's on the outer edge. So what we're saying here is effectively the inside edge becomes a little bit more positive, and that little bit more positiveness is the amount of positive charge that's come in carried by the sodium ion. Now that more positiveness could equally be a loss of negative charge from that internal surface as a gain of positive charge. And that gain of positive charge, of course, doesn't need to be the sodium ion that came in. It could be other sodium ions, or much more likely, potassium ions, of which there are much more inside the neuron. So when the sodium ion comes in, it generates a charged redistribution, which causes the membrane on the inside edge to become a little bit more positive, potentially through a gain of some sodium, a gain of some sodium, or more likely some potassium, and maybe the loss also of some chloride. Okay, so this movement of charge and the sticking to the cell membrane is what gives cell membranes their capacitance, and it generates the electrical field, and it's that electrical field which then progresses along the nerve fibre membrane to generate the voltage change further along. Anyway, I hope that was clear, and thanks for listening.